Okay, what we have here is partial fraction decomposition. So this is a trick that we picked up in pre-calculus, but it can be a little bit challenging. I'm going to show you some ways that you can work through this, but pay attention to the smaller details because that's where you can get tripped up, and there is a pattern. So if you don't see this at first, hang in there. You'll catch it. Okay, so if f of x is equal to the rational expression px over q of x, where p and q are polynomials, the degree of p is less than the degree of q, so the top degree is less than the bottom degree. And as long as q can be written as a product of distinct linear factors, in other words, q can be factored out, then f of x can be written as a sum of rational functions with distinct or unique or different linear denominators. So write the given function as a sum of rational functions with linear denominators. Well, the first thing that we have to do is factor out the bottom. And so to do that, just go back to your algebra 1 and 2 days of factoring. So this has got to be a 2x here, and this has got to be x here. And we want negative 7, so in order to get to that, we're going to have to do 2 times 3. And since the 3 is positive, we're going to have 2x minus 1 and x minus 3. So the problem we want to work from looks like x minus 13 over 2x minus 1 times x minus 3. All right. And what we want to do is we want to set this up as kind of unique pieces. So kind of how this is going to go is that we're going to want a over this linear factor 2x minus 1 plus b over the linear factor x minus 3. So this is the setup that we're looking at here. Okay? And if I'm going to add these two guys up on the right so that I can get x minus 13 over the two guys on the left, notice that I need a common denominator. And in order to get a common denominator, I have to multiply the a by x minus 3, and I have to multiply the b by 2x minus 1. Okay, that gets me my common denominator. So, you know, this is all about just adding the fraction together. So what I'm going to be working from, another thing to keep in mind here is that a times x minus 3 plus b times 2x minus 1 over 2x minus 1 times x minus 3 is the big fraction that I'm working with. Okay? And using my equality, if I have x minus 13 over 2x minus 1 times x minus 3, if this is what I have, then the bottoms have to be equal, which they are. And the tops have to be equal, which is what we have to discover. So what I'm going to do is set my tops equal to each other. And I'm going to have x minus 13 equals a times x minus 3 plus b times 2x minus 1. Okay? And the easiest way to do this is to just ask yourself, all right, if I look right here in this spot, what value of x will make a 0? And so the answer you should come to is x equals 3. And the reason we like that is because if this guy's a 3, this guy's a 3, and this guy's a 3, then my middle term, that a term, completely goes away and the only variable left is b. Check it out. I'm going to have 3 minus 13 equals a times 3 minus 3 plus b times 2 times 3 minus 1. The a term is gone. So negative 10 is equal to 5b. So b is going to be equal to -2. There's my first guy. Well, if I'm going to do that, I also want to then go, what value of x will make my b term go away and give me a 0 there? And the answer is 1/2. So I do this again when x is equal to 1/2. Okay? And when I put 1/2 in for all the x's, I get 1/2 minus 13 equals a times 1/2 minus 3 plus b times 2 times 1/2 minus 1. Okay. Now work this math out. And again, it's not horrible now, because if you look over here, the b's are going to go away. We like that. And so that just leaves us then with working the 1/2 minus 13, which is going to be -25/2. And that's going to be equal to 1/2 minus 3, okay, which is -5/2 times a. And so when you multiply both sides by that -2/5, then everything cancels out, and what are you left with? A equals 5. So if you look back up to the top of the page where we started our problem, okay, if you look back up at the top of the page, we're trying to answer this question right here. Let me get a fatter marker. We're trying to answer this question right here. And so my solution for this is when we've discovered what a and b are. And so my answer then, as a partial fraction decomposition, what we're doing, the answer is going to be that a value, which is 5 over 2x minus 1, plus the b value, which is -2, over x minus 3. This is your partial fraction decomposition. Now, most books won't show you this as their answer. What they will show you is they will move that negative from the 2 in between the fractions. And so this is how you would work out a partial fraction decomposition. Okay, so now keeping in mind that we want to differentiate this, what we're going to have to work with now, is we're going to have to use our partial fraction decomposition. I forgot my dx when I set this slide up. We're going to have to work with partial fractions. The first rule was, though, that the numerator on the top had to be less than the numerator on the bottom. And if you'll notice on this one, that's not true. So the first step we have to take is to check the degrees. And we'll see that the degree on the top is larger than the degree on the bottom. And since that's true, what we'll have to do is long division. So I'm going to have x squared minus 1. And I'm going to run into this 3x to the 4th. And then all the way over here plus 1 in case we need some middle terms. Okay? And so what times x squared is 3x to the 4th? And the answer to that is 3x squared. So 3x squared times x squared is 3x to the 4th. 3x squared times -1 is -3x squared. And since this is division, I'm subtracting that whole thing. And this will be a common mistake. When you subtract the whole thing, you are subtracting this -3x right here, 3x to the 4th, and you're subtracting -3x squared, which is going to actually make this a plus. So we're working with 3x squared plus 1. Now, what times 3x squared, or well, I'm sorry, what times x squared is 3x squared? And the answer to that is 3. So I'm going to have 3x squared minus 3, and we're subtracting the whole thing, which means a minus here and a plus here. So what am I really taking an integral of? I'm really integrating 3x squared plus 3 plus 4 over x squared minus 1. This is what I'm really going to integrate. And that's okay. This is not a problem. The first two pieces will integrate very nicely. We've done a lot of these types of integrations already, and so finding the antiderivative of these two guys is not a problem. The problem is the last part, okay? Because we can't do this by parts, we can't do this by substitution, it won't quite fit in a logarithmic integration, and so what we have to do is by parts, or not by parts, but by partial fraction decomposition, we integrate it. So let's go ahead and start working some of this out. If I integrate the first piece, I'm going to have 3x cubed over 3 plus 3x plus the integral of 4 over x squared minus 1 dx. Okay? But the 4x squared, 4 over x squared, this guy right here, what we really need to think on him is the integral of a over, can you factor that bottom? X plus 1 plus b over x minus 1. Can you factor the bottom? Can you see that? X squared minus 1 is going to be x plus 1 times x minus 1. Okay, so this is really what we're going to integrate. And all of this is going to be dx. Okay, don't panic. What we'll do is we're going to use what we just saw about partial fraction decomposition, and we're going to work this guy out. Remember, you have to have a common denominator. So this a needs an x minus 1. This b needs an x plus 1. Okay, and so what I've got is, what I'm going to work with is that 4 is equal to a times x minus 1 plus b times x plus 1. This is what I'm going to work with. Okay, so just go ahead and set up for our two cases. The two cases in this example would be when x equals 1 and when x equals negative 1. Those are the two instances that will give us the zeros that we're interested in. So on this first guy, 4 is equal to a times 1 minus 1, that's going to go away, plus b times 1 plus 1. Can you see where this is headed? So what I've got is 4 is equal to 2b. So my b is going to be 2. All right. The second part then, 4 equals a times negative 1 minus 1 plus b times negative 1 plus 1. And so, can you see where this guy's headed? 4 is equal to negative 2a. So my a value then is negative 2. So when you're working this out, even though it's going to take a lot of work here, the work itself is not hard, it's just the algebra. But what we're going to end up with is working the integral then of negative 2 over x plus 1 plus 2 over x minus 1 dx. And these are really not bad things to integrate. They're just going to be the natural log of whatever is in the denominator. Okay? And so to sort this out, what you're going to end up with is, let's go ahead and make our page a little longer. When you integrate this, you're looking at You can factor out the 2's. You could even look at it in pieces, like negative 2 times the integral of 1 over x plus 1 dx plus 2 times the integral of 1 over x minus 1 dx. And so when you do that, what you're going to end up with is negative 2 times the natural log of the absolute value of x plus 1. Remember, a natural log can only be positive or it won't work, and then plus 2 times the natural log of 1 over x of the absolute value of x minus 1. So that's how this guy integrates. And what we will do is we'll just bring down our 3x and our x cubed. And so here's your answer, plus c. Well, this is kind of a clunky looking answer. And so usually what we would want is we'd want to clean this up just a little bit. And use your rules of logarithms. You can use your rules of logarithms to do this. If I subtract 2 logarithms, it's the top log minus the bottom. And if you'll notice right here, I've got a negative 2 log x plus 1 and a positive 2 log x minus 1. And it's the positive log minus the negative. So what we could have, which is actually the easiest to see visually on paper, is x cubed plus 3x plus 2 times the natural log of the absolute value of the top minus the bottom. So it's going to be x minus 1 over x plus 1 and then plus c. So this is a weird answer for what we're used to. It's a good answer. The process is long, but the integration is easy. So work this problem out again on your own right now and see if you can get back to the exact same answer. And if you can, you're ready for the next part. Okay, so we're going to find a general solution to a differential equation. And remember, when you're looking for a general solution to a differential equation, you're going to have a plus c value in there somewhere. And you could also, to get a general solution, you could look at a slope field of this on your calculator as well. And sometimes those are really interesting to look at because it gives you just a kind of an idea of the shape of what a specific solution would look like. Well, this particular problem is going to take some pencil work because our denominator is quite large. And you'll notice real quickly that the degree on the bottom is larger than the degree on the top. So what I'm going to do is just kind of rewrite this guy so that we can see exactly what we're dealing with, because it looks like it's possible that we're going to have an a, b, and c term. When I factor x squared minus 4, that gets me x plus 2, x minus 2, and then x minus 1. So the problem that I'm going to be interested in solving out is going to look something like this. So it's going to be partial fractions, but it's going to be over all 3 pieces. So a over x plus 2, b over x minus 2, and c over x minus 1. So, the problem that we're interested in then, the actual calculus problem we're interested in, we're going to multiply both sides by dx. And we're going to have dy equals 6x squared minus 8x minus 4 over x squared minus 4 times x minus 1 dx. And then we will integrate both sides. And when you do that, you end up with a y all alone. But now you've got the integral of this problem. And so the integral we are going to solve is going to look like this. A over x plus 2 plus b over x minus 2 plus c over x minus 1. So that's the actual integral that we want to solve out and get a 0 from. So back over here to our partial fraction decomposition, if we look at this guy, the thing to keep in mind is that we want to get a common denominator. So when we do that, we have to multiply the numerators by the pieces that are missing. So a gets an x minus 2, and a gets x minus 1. B gets x plus 2, and x plus 1. And C gets x plus 2, and x minus 2. Okay, so what we're really solving out then is 6x squared minus 8x minus 4 is equal to a times x minus 1 times x minus 2 plus b times x plus 2 x plus 1 plus, let's move all this over a little bit, we need a little bit more space, plus c times x plus 2 x minus 2. Okay? Well, that's a big long thing. And what we have to do is eliminate those variables whenever possible. So in order to eliminate a variable, we just need one of those terms to go to 0. And I'm going to have 3 cases then that I'm interested in. I'm going to be interested in x equals negative 2. I'm going to be interested in x equals positive 2. And I'm going to be interested in x equals 1. So these are the 3 cases that we want to check. And it really isn't too bad now, because one of these terms is going to go away each time, and all the other things will be, or 2 of the terms are going to go away, and that just is going to leave me 1 item to have to check. So what I'm going to do is I'm going to replace x for everything, a negative 2 in for all the x's. So I'm going to have 6 times negative 2 squared minus 8 times negative 2 minus 4 equals, and then a is going to be times negative 2 minus 1, and then negative 2 minus 2. But then look what happens. If I put a negative 2 into this term for b, that whole b term goes away. And when I put negative 2 in for the c part, that whole c goes away. Even though negative 2 plus 1 is not 0, what I end up with on this b term is b times 0 times negative 1. That's a 0, so I don't have to worry about it. And the same thing for c. So my problem cleans up really, really nicely when we do this. And what I'm going to end up with for a is just the whatever times a equals the number on the left. So you do have to pay a little of attention here. I'm going to have 6 times 4, which is 24, plus 16 minus 4. And that's going to be equal to a times negative 3 times negative 4. And what I end up here is, what is this, 36 equals 12a. So for our purposes, on this problem, a is going to be 3. Just divide both sides by that 12. Then, look at when x is 2. So when x is positive 2, I'm going to have 6 times 2 squared minus 8 times 2 minus 4 equals, and now check it out. If I put a 2 in everywhere, when I put in my 2, if I put a 2 in right here, 2 minus 2 is 0. The a term goes away. Okay? When I put a 2 in for b, this is going to stick. So I'm going to have b times 2 plus 2 times 2 plus 1. And then when I put it for c, notice on that last guy, that's x minus 2 over there. It's hard to read, but when I put a 2 in here, that gives me a 0, and the c term is gone. So what I end up with then is 24 minus 16 minus 4, which is equal to b times 4 times 3. Let's move this guy down just a little bit. And 24 minus 16 minus 4 is going to be 4. Alright, I got a little error here. This should be x minus 1, which changes this guy right here to minus 1, which gives us 4 times 1. Which will give us 4b instead of 12b. So in this case then, my b value is going to be 1. And then on the last guy, when I plug 1 in everywhere, I'm going to put a 1 in here. This first term is going to go away. When I put a 1 in here, this guy is going to go away. And so that just leaves me a c. So what I end up with is 6 times 1 squared minus 8 times 1 minus 4 equals c times 1 plus 2 times 1 minus 2. So 6 minus 8 minus 4 equals c times 3 times negative 1. And on the left, I end up with negative 6 equals negative 3c. So in this case now, my c is going to be 2. So what I'm actually going to integrate is 3 over x plus 2 plus 1 over x minus 2 plus 2 over x minus 1. And as we saw in the previous problem, when we integrate that, that works out really nicely. So I'm going to have, when you integrate again, think in pieces. So I've got this piece right here with a 3 in front, this piece right here with a 1 in front, and this piece right here with a 2 in front. Just like on our previous problem, look for the pattern. So when I integrate this, what I'm going to end up with is y equals 3 times the natural log of the absolute value x plus 2 plus the natural log of x minus 2 plus 2 times the natural log of x minus 1, and plus a c at the end. Most texts will not leave their answer this way. If you are adding in between each term, like we are on this one, then you multiply the insides of the logs. So basically what I would have is, and this will look really strange, but the natural log of absolute value x plus 2 cubed times absolute value of x minus 2 times the absolute value of x minus 1 squared. And this is your general solution. The graph y equals as the general solution to the differential equation. Okay, so now moving from a partial fraction into a logistic differential equation, which will require a partial fraction. And this is just one of the simpler problems now. The logistic formula is a great way to model population. And the reason is because it's a more realistic model than looking at an exponential. The graph of a logistic function is going to look something like this, where it's got a lower horizontal asymptote and an upper horizontal asymptote. So when it reaches this top part up here, this top part we refer to as the carrying capacity, or maximum growth. Like, our population can't grow larger than that. So a good example is for logistic growth is if the flu bug is spread through your school. There are only so many students in your school that can get the flu, and then you're out of kids in the school who can conceivably get the flu, and then not everybody will get the flu. So some people, don't get sick. So the logistic model is excellent. The other thing that we need to talk about also is where it crosses the y-axis right here. This is your initial population. This is your initial amount. Okay, and so right here, this would be like our amount initial. All right, and so that's how this guy looks. So if you just think about this, the curve grows and then it levels off. And the formula for this stuff is given to you right here in the pink chart. So here's your formula. Okay, it looks terrible. It is not. Okay, notice that on the left it's a differential equation, on the right it's a function. Okay, so the solution to the general logistic differential equation, dp over dt equals kp m minus p, is this logistic function, where a is a constant determined by an appropriate initial condition, and the carrying capacity m and growth constant k are all positive. Okay, so let's just take an example here. The growth rate of a population of bears in a newly established wildlife preserve is modeled by the differential equation dp dt equals 0.008 p times 100 minus p, where t is measured in years. Okay, so basically, if we were to see this as a fraction, we're going to have dp over dt equals 0.008 p and then 100 minus p. That looks really terrible. Let's refresh. Let's do this again. Okay. So this is actually, how it would look if we were to write it down. So the question then is, what is the carrying capacity of the bears on the wildlife preserve? And if you look at your formulas, the carrying capacity is that number in front of the p. So part A here, if we label these A, B, and C, part A, the carrying capacity is going to be 100 bears. Like, the park, the wildlife preserve, can sustain 100 bears, and then after that, it's just not possible. Okay. Part B. Now this is a tricky one, and it's going to require a little bit of intuition. What is the bear population when the population is growing fastest? Okay. What is the bear population when the population is growing fastest? Well, if you look at your logistic curve up here, where the population is growing fastest, remember, we've got a lower boundary. Okay, we've got this lower bound, down here. We've got an upper bound up here. And so where the bears are going to grow quickest on any logistic function, you're going to have your population changing the most when you are halfway to the carrying capacity. So anytime you're asked about the fastest growing is going to be when you're halfway to your carrying capacity. So it's half the carrying capacity. And half of the carrying capacity of this particular question is going to be 50 bears. Okay. The second thing that we want to know is what is the rate of change of the population when it is growing fastest? So remember, anytime you look at a derivative, which is what this is telling us we've got a derivative, you're talking about a rate of change. And if we know what the population is, which is our p-value, then all we have to do to find that rate of change is substitute what our population at that time is. The question for us is, what is the change of population, which is dp dt? When it is growing fastest, well, we figured out that that's going to be at 50 bears. So dp dt is the rate of change of my population. I want to know what this is when I have 50 bears in my population. So I'm just going to plug in at 50. And I'm going to punch this into my calculator. So when I do that, turn my calculator on. I get 20. So what does that mean? 20 what? Okay. Well, we're talking about t in years. So my population is changing quickest when we grow by 20 bears per year. Okay. And so that's kind of the basic way that you would use this logistic model. All right, so in 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from Algonquin Park, Ontario, to Marquette County in the Upper Peninsula. It was originally hoped that the population would reach a carrying capacity in about 25 years with the given growth rate, and then they give us this differential equation. And according to the model, what is the carrying capacity? So this is not a hard thing to discover. The carrying capacity is going to be that number right in front of the p-value here. So again, like on our previous problem, if we call this A, B, and C, then our carrying capacity for this is going to be 1,000 moose. Will be our population maximum. So 1,000 moose is the carrying capacity. Okay. Part B then says, with a calculator, generate a slope field for the differential equation. And I'll add that in here so that you can see what that'll look like, and I'll let you look at it here for a second, and then I'll make it a little bit smaller so we can keep doing the math. But you've got your slope field here, and you can either use the TI Inspire, which is what I did to generate this, and the TI Inspire is a great way to look at a slope field, or you can run a slope field program on your TI-84 and look at it that way. Part C then says, solve the differential equation with the initial condition that P of 0 is equal to 61 and show that it conforms to the slope field. So now what we want to do is get our variables separated out. So notice that I've got right here, I've got P's, and right here I've got T's. So those guys have to trade places. I can't work this problem the way it is with them on those sides. So what I've got is, when I do that, I have dP over P times 1,000 minus P equals 0.0003 dt. And if you'll notice, what I've got on the left is a partial fraction decomposition. The right side integrates very nicely. There's really no ginormous trickeration on the right. But the left, on this left-hand side, we've got to run through our partial fraction decomposition and just look at what's going on. So basically what I'm going to work with is that A over P plus B over 1,000 minus P is equal to 1. this is the equation that that I'm going to work with. So how does it really sort itself out? Well, it's A times 1,000 minus P plus BP equal to 1. And so I pick my very specific values of x here. I'm going to let x equal 0 in one instance, and I'm going to let x equal 1,000 on the other. Okay? And what this is going to do, when x is equal to 0, I'm going to have a times 1,000 minus 0, and b times 0, 0 equals 1. So in this case, I'll move this guy down just a little bit. In this case, then, a is going to be equal to 0.001. Okay, because 1 divided by 1,000 is what this one's going to end up being. Okay. Then on part B, with 1,000 here, what I'm going to have is 1,000b equal to 1. And so this is going to be b equals 0.001. So a and b are exactly the same. Well, what does that mean for us? That means that the integral that we're looking at, when we integrate both sides, what we're going to end up with is the integral on the left will be 0.001, okay, over p, plus 0.001 over 1,000 minus p. And on the right, we're going to end up with 0.0003 t. So that's not too bad. Okay. Sorting this out, on the left, we're going to have 0.001 times the natural log of p. And remember, p has to be positive, and in this particular problem, we're talking about a population, and all populations are going to be positive. So we're going to not use the absolute value bars because we are dealing with positive numbers. And then the natural log of 1,000 minus p. And remember that we just need plus c. We only need that in there one time, okay? We only need that guy in there one time. He's a constant, even though we're dealing with him on, on both sides. Everything is going to be okay. And one thing that I like to do is to get rid of nasty little decimals. So if you'll notice, everything's a factor of 1,000 here. And so if I multiply my whole side on the left and on the right by 1,000, okay, that's going to get me to ones. And so I end up with the natural log of p times, let's see, the natural log of p plus the natural log of 1,000 minus p is equal to 0.3 t. And remember, the c is just some constant which we don't know, so it looks like this. By the way, I've made a small error. Once you integrate, since I've got a negative p down there, I have to account for that. My negative p right here is going to give me a negative sign in front of my natural log. Think the chain rule here. If you're not sure, remember the chain rule. So that means this guy also is going to be negative. Alright. And so what I end up with then on the left, I end up with natural log of p over 1000 minus p, and that's equal to 0.3t plus c. Okay? Now, we're going to use some little trickerations of mathematics here. One is I'm going to rewrite this as a logarithm, or as an exponential, so I can get the variables that I want out so it's easier to work with things. Okay? And so what I'm going to do is I'm just going to rewrite this. Remember, natural log is a log base e. So that's going to give me e to the 0.3t plus c power is equal to p over 1000 minus p. Okay? Just using my logarithms. And the rule I'm following is, in case you don't remember, a log base e is equal to a natural log. And so if I have a natural log of x equals y, then e to the y is equal to x. So don't forget this. Okay. And then once I'm here, I've got that initial condition that has to be met. And they're telling me when p is 0, t, my population is 61. Okay? When t is 0, my population is 61. So now what I'm going to do is just substitute in t equals 0, and I'm going to substitute in for p 61. Okay, now in order to match up with our population model, what I need to do is have my e to the power of 3t plus c, I need it to be negative. Okay, so it matches my rule that we established on the previous page. So to do that, I'm just going to look at the reciprocals of both sides. And when I look at the reciprocals of both sides, I get e to the negative 0.3t plus c is equal to 1000 minus p over p. So this is going to allow me to match. And the important part is that my exponent over here is negative. This is what I'm looking for to match my logistic model. Okay? And so this is a trick that this is a step that if you do incorrectly, you're going to wind up with a negative initial amount, and or a negative constant down there in the denominator where the a is, and we need that value to be positive. Okay, and so now I can simplify this by substituting in my values for t and my values for p. So e to the negative 0.3 times 0. And by the way, I got a little typo right here. This should be a minus c as well, because he also was in the denominator. And we want to leave them in green still. So we'll do this to make sure we're still in green. Okay. And, okay, so I've got this. Minus c is equal to 1000 minus 61 divided by 61. Alright, no problem. So on the left, I have e to the negative c. And on the right, I've got 1000 minus 61 divided by 61. So e to the negative c is equal to 15.393. And, you know, if you're paying attention, from our rule that we wrote down, I need this value. I need this e to the negative c value. Okay? And so what I end up with then is my population model follows this logistic rule that we looked at the beginning of the problem. And so now it's going to be that p is equal to, and this is my initial amount now. We've solved for that c value, this guy right here, this c value. Okay, and so when I follow my rule, I can substitute all of this stuff in, and it's going to look like this. I'll go ahead and show you the long way here, and then we can shorten it up in a minute. But it's going to be 1,000 over P is equal to 1 plus 15.393 e to the negative 0.3 t. So there's my negative 0.3 t part. And then when I solve this for p, I wind up with p equals 1,000 over 1 plus 15.393 e to the negative 0.3 t. So it's a long process. It's doable, but you know, the algebra, if you go one step at a time, the algebra is not too bad. Don't forget that step highlighted in green. We've got to have that part so that you can get the right answer at the end, so that it matches up with our general logistic formula.